In the previous class, we learned about what we call about wave, right? We learned about how technology correlate with the wave and how we can use wave to help us to probe into the world of unknown. For example, to know the structure of DNA, you use SRD, which utilize the X-ray wave. And in order to transmit the signal from your phone, you use a radio wave. In order to kill the bacteria in the lab, you use a gamma ray in order to irradiate the thing. So today we will dig deeper in the wave story again, but this time we will start with the categorization of the wave, how you categorize the wave. So we have wave here, okay, let's say we have wave here, and then we want to try to categorize the wave. You can categorize the wave in two different ways. The first way to categorize the wave is that you want to see whether the wave can travel or not inside the vacuum, okay? So, basically, the one that can travel on the vacuum, if let's say the answer is yes, the answer can be also no. Okay? So, the wave that can travel in vacuum, we call it as what we call the one that cannot travel in vacuum, we call it mechanical wave. Mechanical wave. This is the name, the category lah, for those wave that don't travel in vacuum. And example for this is basically the sound wave lah. The sound wave, you cannot, for example, if let's say you have the bell ringing, let's say you have the clock, and the clock have a, what we call, bell on it. And then if you put this clock inside the what we call inside the vacuum jar, you will you cannot hear the what we call the ring lah, vacuum jar, whatever. An example of the mechanical wave is for example the water ripple. Water ripple. So you throw a stone into the pond, you can see the wave rippling outright. So that require the what we call the medium. So the medium there is basically water. Okay, so that is basically the type of mechanical wave. They require a medium to travel. For example, this sound wave requires maybe air, it's like gas, so that is also medium. Because the medium can be either what we call air, the solid, or liquid lah, or liquid. Same with water ripple, it travel in the liquid. If the wave can travel in vacuum, we call it, typically we have the name for the wave, not the name, I mean that it's not like the specific name, it's just like the wave that can travel in vacuum is electromagnetic wave lah. Okay. So we learned before, example of electromagnetic wave is what? From big wavelength to the low. Radio, and then what else? Huh? Sorry? Gamma. No. From top, from the highest wavelength to the smallest wavelength with the order. From radio, and after radio? Micro after micro? Infra after infra? Visible first. After visible, UV, and then after that, X-ray, and then after that is basically the gamma lah. So this is a type of what we call the wave that can travel under vacuum. We call it this everything is electromagnetic wave. All these things, the difference between all these things is just in terms of wavelength lah. So we have wavelength here, wavelength. So we put gamma, this lambda lah. So the difference is just that. Those who have like higher wavelength, for example, this you have a wave, and then the wavelength is basically the distance between the peak to the peak. For example, from here to here. So this is basically the wavelength. So the difference between all this is just the size of the wavelength. For example, if you have this and compare this to something like this, so you can see, let's say this A and then this B, and A and B travel in a certain equal distance. For example, let's say from here from here to here is basically maybe 1 second. So we say that the B is more energetic because you can fit more wave into the into the region lah. So this wavelength is here lah. So this wavelength, okay, the lambda. Okay, we put lambda here. Okay. So from this, there are also features that you can see also. So this is wavelength, and this, if let's say you make a middle here, let's say I make a middle here, make a middle distance here. Let's say this here, okay. So the difference between here and here is the amplitude. The difference between the middle line to the highest peak or lowest through. This we call it crest lah, crest, and then the bottom one we call it through whatever lah, what one nak pronounce saya tak tahu. Anyway, the distance from this and this is what we call amplitude from here, not the overall from here to here only. So this is basically we call it amplitude. How strong the wave. Okay. So this is second, let me put second here. Okay, so that is basically electromagnetic wave and mechanical wave lah. So you can categorize the wave by which whether they can travel in vacuum or not. Another way to categorize the wave is in terms of direction of medium, medium travel in the direction of a wave, in medium travel in the direction of wave direction is quite wave propagation lah, propagation. Okay, so the second way how to categorize the wave is based on how the medium itself travel. For example here, the sound wave, the medium is the air, right? If let's say you say like this, the medium is the air. The water ripple, the medium is the water itself. So that's what I mean by the medium here. So here, the medium here is basically the electro and magnetic. You know what we call the electromagnetic wave. All these things, they have like all these things. They have this thing. This basically you have something like this, and then you have one wave goes like this, another wave goes to perpendicular like this. And this 3D, you know like this 3D, right? Yeah. So imagine this is you have like 3 axes, up, front, and the side. So this is the from here, and from here. And then this is basically perpendicular with each other lah. The red one, the red wave, which is maybe magnetic or electromagnetic, is basically mean you have magnetic field. So let's say the red one, and also the electric field, the green one. So this is electric. This is electric field. Electric field. So this electromagnetic wave composed of two things. The magnetic field and electric field combined together at what we call perpendicular angle. So the medium for this electromagnetic wave is this lah, the magnetic field and also electric field. So this second category, you want to categorize the wave by which the medium travel, how the medium travel along the wave propagation. For example, the medium can travel either parallel or perpendicular. So if I make here, and make here, let's say parallel, and this is perpendicular. Okay, example of parallel is like when you have, for example, like what we call the sound wave, like we learned before, when you have somebody here, and then somebody talk, and then they have what we call, they vibrate the particle, the air particle around him or her. So the particle will be compressed or decompressed. Okay, so this is the thing. So this, we learned in the previous class that the compressed one we call just a compressed region lah. Compressed region. The decompressed region, what we call it? The decompressed region. This decompressed region. Huh? Sorry? This one, what we call the region where there are less, what we call less molecule compressed together. Rarefaction, Rarefaction. Rarefaction, Rarefaction. Fraction. Okay, it's like macam you buka pintu ni. You buka pintu ni. Sometimes bila you buka, what we call the air is coming in, right? The air molecule is coming in. If let's say here there are like windows with the what we call with the curtain. When you open this thing, what will happen to the curtain? Let's say I open the door. This door, let's say this door, this door, this door, and then this is like say you have a window, and then you have a curtain there. You have the curtain here. Let's say you have the curtain here. Okay. If you open the door, let's say you open the door, what happened to the air molecule? If you open, let's say you open, so the air will go to here, and will push this curtain outward, right? We push the curtain outward. Somehow will go. This curtain will go here. Will go some here lah. Will go like that. So this basically you try to compress the air. What happened then later on if let's say the curtain is flat again to the window and then you try to sort of like push out. I mean push out ke push in. Close the door. So basically there are region of low pressure in the middle. So this curtain will somehow feel like it will go toward here. If let's say you, I cannot copy paste lah. I need to draw again. Yeah. That's the problem with the physical class. Online class, I just copy and paste this thing. And if let's say you have this thing, let's say I close this to make it clear lah, the curtain lah. To make it much clearer lah. If not, they are confusing. Okay, so the curtain somehow we push outward lah. But in this case, in the second case, you have this window. If let's say the curtain at the beginning stay flat on this, if this window is open at, initially and then you try to close, you create sort of like the low pressure region here, and this curtain will sort of like goes somehow will sort of like vacuum inside. You create a vacuum, sort of like vacuum lah. You create a vacuum, but this time it's not like totally vacuum like your vacuum pump, vacuum at your house. So basically this is what we call rarefaction lah. There are less molecule here. You sort of like bring out the molecule out by the act of closing this window. So that's happening here lah. That's happening here, the compression and also rarefaction. So this, if you look here, the air molecule is here, right? And you can see the direction of this. They're moving what? They're moving in one direction to the right. So you can see the what we call the particle and also the direction of the wave, because this direction of the wave move in one way, parallel. So this is what we call the parallel, or the other word for this is basically we call it longitudinal wave. Okay, so this is the name for this the wave that is travel like this is longitudinal wave lah. The name. Example is basically your sound wave lah. Sound wave. Okay. So it's like you have a slinky. Pernah main slinky? Slinky tu saya ada. Guys, ada. So slinky like this. Slinky like this. You try slinky kan? You try like that. So you have. If I try to do like this, is you know that I pushing downward, right? You know I pushing downward, and that the wave is not. Is basically. It's not really the particle that is you push the particle. Is the wave itself. For example, let's say I hit this thing. You can hear there. The particle doesn't move. The particle in this board doesn't move, but the wave that move, same like this. this solid here, this yellow color doesn't really move forward. The color still stay right. The middle is green, and what you call the bottom one is orange. So the top color doesn't really go down, but the wave. So that's the difference between wave. You don't, that particle here is move lah, but it's not really, when you talk, the particle here will go all the way here. It's the wave that you carry out. So that's why we say that if the medium travel in the direction of the wave propagation, we say longitudinal. This medium, yes, it's travel, but it's not like from start to finish. It's like the wave itself is you bring the wave, you propagate the wave. Okay. So perpendicular is basically, as the name imply, is perpendicular lah. So it's like you are doing this like this. Dua orang, sebab saya lepas ni saya nak terangkan something. Siapa tak lagi? Erika. Dengan siapa lagi tak pernah? Rifdi, sini. Okay. So seorang pegang sana, seorang pegang sini. So basically perpendicular because I need two person because I want to explain also the third category of the way how the wave ni lah pegang. Okay, pegang. Okay. The middle. Kenapa macam ni? Betul kan? Betul kan? So basically while they repair this thing, the perpendicular wave is basically is like, what is the example of perpendicular wave? Stay, Rika. So basically, when you try to drop a stone into a water, what will happen? You get a ripple, something like this, right? Something like this. So the stone goes down. This is the water. Okay, stay dulu lah. Duduk di situ. Duduk atas meja je. So because if you look here, the wave coming out, right? The wave coming out. This is the direction of the wave. The wave coming out. But if you look at the at the water itself, the water up and down, right? It's not following the wave, but it's perpendicular to wave. So that is what we call the perpendicular, or other name for that is, siapa tahu? Satu markah. Siapa cakap tu? Okey, Tania. Tania. Okey, senang je dapat markah. Transverse wave. Transverse wave, whatever lah. But you know that. So basically this, they go up and down, right? The water molecule go up and down. So example, what dah? Rifdi and Erika. Okay. So Rifdi, Erika just stay like that. Rifdi buat je ni. Okay. So basically, you can see when Rifdi try to move, give the energy. Basically, what Rifdi done now is giving the energy to this slinky. So now Rifdi give the energy from here. Erika just stay put. So you can see the energy come from here to here, but you see the direction up and down. There are certain time that if let's say Rifdi can give exact a certain amount of energy, something will happen here. If you do now, just do like normal ya. Macam tak nampak apa-apa kan? Just up and down only. But just stay. They are a third, not category, but it's just a special category. They call it standing wave. Standing wave is basically as if the wave freeze in the motion. For example, if the Rifdi do, just normal. So you can see the wave up and down, go here and go there. Buat dua lah, ni satu je. Kuat sikit. So it doesn't really matter, but what you can see now is basically you see the wave coming from Rifdi to the Erika. The standing wave is as if, even though Rifdi give the energy, as if the wave stay in motion. So that happen only at certain frequency. Certain frequency meaning that you move up and down. So you can see down. Okay, you can see here. So as if in the middle, just slow sikit. Because saya nak buat yang first dulu. Cuba buat, ada tengah ni berhenti. Cuba buat. Tak, Erika stay je. Okay, you see ya? Okay, like this. Maintain this energy because the energy must be maintained. What Rifdi does now is that Rifdi give specific energy because you give energy to the wave, right? So now it's as if this middle is what we call static. So the wave up and down in one direction only, because if you look, stay lah. Okay, if the idea is that the wave, they continues moving, right? They continue moving. But in this case, as if you have the wave contained in two, what we call, two pole like that, you can create the standing wave like this. Okay, this standing wave only happen when RIFD maintain this energy. You can create another one. Okay, this is, you have this in, okay, maintain. Okay, in the middle here, itu saya suruh RIFD buat sebab dia lelaki. So if you see here, maintain je lah. Okay, so you have something like this, right? You have middle ground. Maintain lah RIFD. Exercise. Okay, so you have something like this. Okay, so in the middle here, what seems like freezing here is, we call it node, and this is antinode. Okay, so this thing will only occur at certain frequency only. The next frequency you will see 3. You will see the next frequency, you will see 3. You will not see 2.5. The next frequency you will see something like this. Something like this. In the same ni lah. Let's say I put in the same distance. Okay, because that thing is the same distance. Okay. The next thing, if let's say RIFD give more frequency, more energy, what will happen is that this will, you can see 3. Not 2.5, not 2.7, whatever. They must be 3. In between that, nothing happen. So cuba 3. Ni 2. Ni 2 Ni 2 lagi. So it must be certain frequency only. What 3? This is only 2. Just maintain the distance. In the beginning, you can do 3, right? So in the beginning, RIFD did very fast. It's not how strong you do. It's about this. You see. Tak cantik lah. Cantik sikit. So this what we call standing wave. Cantik lah. 1, 2, 3, 4 lagi. So it needs certain frequency. This also what we you do sampai dapat. So this, when you get this, the static standing, you get what we call resonance lah. Resonance. Okay. So still 2. 1. Sah kan? So it's not like nampak macam easy, but this is where the notion of only certain energy can give that. It's not like while you do this you always get. It's always certain. Tengok sekejap, saya pun tak tahu je. Yeah, you see that? Nampak? You have nampak? Saya pun tak tahu. Nampak? So you get this thing. You have three what we call? Three apa panggil tu? 3 half wavelength. Because this is wait. So 3 half wavelength. This is the first. Okay, the first. So you see my hand, I give the frequency, exact frequency. Every material in the world have their own frequency. If I drop this thing, you can see the sound, right? So every material have their own vibration. So you can differentiate between that and I drop this thing, you can see the sound is different, right? So that when it hit the floor, it have their own frequency, it vibrate at their own frequency. So every material have its own frequency, like this also slinky. If I can fed my what we call my hand, fed the energy that is equal to the frequency or natural frequency for this, then you get resonance. So like this lah. So meaning that when I do this thing, I fed the energy in such a way that is sort of like equal to this. It's not about the slinky, it's about the way how I up and down lah. Because the slinky is this only. What I do is that the it's different to ni lah. But at least you get the idea lah. So this is one. The second, you need to. It's not about how fast you do. It's about the correct ni lah. The correct. What? Erika buat. You buat. Dah lengur tu. Buat. Cuba buat. So that's 1, 2, buat 3, cuba buat 3. So when you want to go to another level, it's not about how fast you do, it's about the correct intensity. What Erika did is just increasing the amplitude. Increasing the amplitude, it doesn't doesn't goes from one level of standing wave to another level. You need to still in one. So it just need to be like certain frequency. So just like that. Okay, thank you. So basically that is basically the standing wave. Standing wave, as I said before, is unique. You need to have exactly at the note, not exactly at the note, meaning that you either have, this is what we call, let's say this is what we call half wave. This one is half wave, half wavelength. So it always occurs in integer mode lah. For example, you half plus half plus half plus half plus half. It cannot be like in the middle. Because wave, one of the properties of wave, if you have something like this, and then you plus something like this, you get like that. You cancel each other. This is what we call the interference or destructive. This is what we call interference. Interference. Okay. So if you have two waves, the one is top, another one is bottom, combined together, you get this destructive interference. This is what we call destructive interference. If you have something like this, plus this, you get a much bigger thing. This is what Erika did just now. They increased the amplitude. They increased the amplitude only by doing like this. In order to make standing wave, you need to the frequency, how fast. It's not how intense. This is how intense. This is how fast. So that's make a difference. So this what we call the constructive interference. Constructive interference. Let me explain a little bit about this standing wave. This standing wave happen is because if let's say you have this rope, let's say just now Slinky, this is Erika, okay, this is Rifdi, this is Erika. Okay, what happened is that when Rifdi, this rope like this, normal, when the Slinky is it's like this. When Rifdi start to propagate the wave start from here. So you can see something like this, right? Something like this. And then this wave goes forward to Erika. So you can see now, instead of here, now it's here. Here, you get in the middle. And then, later on, we got here. And along the way, when Rifdi goes up and down, at the same time, there are another wave coming here. Because Rifdi not do like this only, you just do up and down. So that's why you have another one here. So at one moment when the frequency is right, what will happen is that this thing, when you have something like this, this wave coming to Erika, it will bounce back. So at least you get something like this. And then this goes something like this. Okay? So like that. So you see, this is reflection of the wave. One of the properties of the wave, you can reflect lah. So at one moment, if this energy is correct, this thing and this thing will superimpose with each other. That's why you see that what you call? This thing, you get this thing, and then at one moment you get something like this. This thing superimpose each other because let me put a different color lah. Much easier. Where is my red? Oh, I throw down. So you can see here. So this thing, let me draw a different color. Okay. If the energy is right, this red and blue will superimpose each other. Because of this destructive interference, you will get nothing here. You get something like Nothing. This is where the note, where is the note occur. Okay, the note occur. This I show only one, but when you do like this, there are multitude of wave occur. Multitude of wave coming in and down and so on. So that's why you will see something like this and note, something like that. So the note here, this is destructive happen here. So that is happen when you have two rope or whatever in the, what we call, in the constrict by the, bounded by this pole lah, 1 and 1 lah. So it can reflect, and by reflecting here, but when the wave reflect, it will meet with this another wave coming in, and then destructive interference occur. And when the frequency, the energy given is correct, then you get this standing wave. The standing wave, the other waves, the other, not name lah, mean that layman, they call it resonance lah, resonance. So it's only occur at certain frequency. So this is in one dimension. In two dimension is more, what I call more complex. Okay, more complex. This one dimension is easy. You can see like this node and dot. So in second dimension, let's say I have this. For example, siapa nak panggil? Tak yalah. Let's say I have this and I have this speaker. I have the speaker. Let me open. So I put this thing here. Siapa nak Umi lah sini, Umi. Sini Umi. You pegang. Saya malas nak letak. You pegang macam ni supaya dia orang nampak. Okay. So okay, nah. Pegang supaya nampak tu. Okay. So I will put the image here. So the camera here. Camera, let me open this first camera. So this in the second dimension. Okay, Umi, mana Umi? Tu Umi. Okay. Okay, dekat atas. Tak apa, nanti saya panggil dia. Okay, let's say this is a Bluetooth speaker. This is Bluetooth speaker. Before I show this thing, okay, Umi is okay. I want to show you something else. Let me go to this thing. When I said in the previous class about the frequency, I want to tell you first, before we do this experiment, I want to show first about the, what we call, see me. I want to show you first, what does it mean by this frequency for wave. So for that, I will bring this thing to here, bring the Google here, and then I put, what I want to put, online frequency. Online frequency. No, internet, let me open the internet first. Okay, stuff, connect, and then, okay, the internet, okay, enter, okay, online tone generator, okay, let me open this thing, okay, so this, from here to here, this is 20, right? Our human ears can hear, okay, because we talked about the sound previously, and we talked about decibel and so on. I talked about decibel in the previous class about the pressure, sound level pressure, which in Pascal. This hertz is what normally you see in here. When you see this thing, let me make it smaller first. When you see this goes here, this hertz, this thing is basically the vibration lah. So to appreciate how is sound, so you can just go to online and go to this online tone generator. So this until 20,000 hertz only, because this is what our ear can hear lah. And this is no hertz lah. If I play, if I go up, wah, saya kena buka sound. Okay, dah ada sound tak ada sound Oh, jap ni. Wait, speaker. Can you hear the sound? It's quite. Wait. Can you hear the sound? Okay. Because that I don't know how to connect with it. I connect with the phone only. Anyway. So this. Can you hear? You think? Dengar Ikmal. So 600. Okay, so that is after 200,000 and above we cannot see. This is what is the region is ultrasonic, where the bat, dog can hear lah. So in fact here, there are vibration. Vibration meaning that this thing, frequency of the speaker, when you have a speaker vibrate, the diaphragm will up and down, up and down, up and down, right? So that is what basically the hertz is. Basically now the speaker in my dia ni letak atas ni je lah. Tak ada. Okay, so basically the speaker, they are basically pushing the air 2,000 times per second at this moment. The speaker inside my this lah, they what we call, they push air like this lah, 2,000 times per moment. So you cannot see, you cannot hear. So it doesn't mean high number of frequency you can hear. Okay, so this is the region where human can hear lah, between 20 to 20 kilo. So that's the region 20 to 20 kilo hertz. Okay, so that's correct. So now we want to do this. So I want to show you how this frequency here is basically you give energy. So now we want to see how it's look in the 3 dimension lah, 2 dimension only. So here is there are like a Bluetooth speaker here. So I connect with my phone. I just connect belum saya tak tahu. Okay, connect. Songkor done. Itulah. Dengar. So basically in this Bluetooth here, if you look here, this is also the frequency generator lah. So here you can see what we call this thing. Can you see or not? You can see up and down. This is 2 hertz. Okay, if I go further, you can see that they are more like that, right? So you can just download in the App Store. So we want to see here what happens. So this is paper. So as I said before, each metal have their own natural frequency, meaning that where it's vibrate. Okay. So if let's say the vibration coming from the speaker match this vibration here, you get resonance. So resonance means they are standing wave there. So standing wave have sort of like specific pattern like this. So if you put like what we call the something like salt ke apa ke, rasa ni, masa ni baru berguna. You tengok macam ni. Sekejap saya nampak. Okay, so let me put here. Saya nak biar you tengok dari atas. Macam tu. Boleh berdiri lah. Macam tu. Macam tu. Okay. Saya malas nak letak sini sebab nanti kena ni. So basically I sprinkle this thing. Just sprinkle what we call the salt. This is just salt lah. Salt. Tu macam ni. Okay, So basically now, okay, you stay there. Nampak tak salt tu? Nampak kan? Banyak sikit Okay. So I do like this in order to make sure there are no preference in term of what we call in term of direction. Everything is homogeneous. So now I take this thing, I try to play this thing. So now it's basically connected. It's 25 hertz. Okay, 25 hertz. Now I go up. So there are some vibration happen, but not so much pattern occur, right? If I go like 2 to 4 again. This adalah. So it's vibrate at certain frequency only. So at certain frequency you will see like the pattern like that. Even though you sprinkle more, for example, you sprinkle more, they will go to what you call to the direction, specific direction lah. If I go up, there are no vibration and you cannot see the pattern lah. Wait, alamak, benda ni. Yes. Come in. Oh, yeah.
Aircon ada problem ke?
Aircon problem ke? Tak tahulah, dia pun tak tahu.
Sejuk tak sejuk?
Sejuk tak sejuk? Sekejap again Okay. So basically, you kena tengah-tengah lah. So this just show you that this paper try to match what we call the the frequency given by the my speaker to the thing lah. So at certain frequency, this is 30. There are no, because 30 still is moving down. If you look here, if you look at the amplitude, it's the same all around. It's not like it doesn't what we call, it doesn't vibrate. It's vibrate. The amplitude is the same. It's not like I change the amplitude. You might say that, okay, this is not vibrate. But if you think, if you look at this, the vibration, the up and down, the distance, the amplitude is all the same until the end. So it's still vibrate, but it doesn't show here anything because it doesn't mesh with the vibration of the paper. If I change this paper with the glass, with the besi metal, it will different frequency that where you get the pattern lah. So for the paper here is around 100 something. So 70. Yeah, it depends. So this is the vibrate the most lah. So normally the best is when you have like a circular speaker lah, because this speaker is rectangular, so it's a little bit difficult to see the homogeneous vibration lah. If this is circular, then you can see a much better pattern lah. So you can just see, for example, they are not just, this is where the note, this is where the amplitude lah. So in 2 dimension, what you see just now is 1 dimension. So it's totally different lah. So you can see this note, this is the what we call the what what note. This is note. This is the anti note. Okay, so it's okay. Thank you. Siapa nama? Umi. Okay, enough for that. Okay, so now you can see that thing. Saya akan tutup dulu. Nanti habis punya bateri. Okay, and then now, what we want to know now. Okay, so once we do that, we can see, okay, now about the, let me close this thing first, so that it doesn't affect the thing. Okay, so you see this thing, okay. Let me go right further. Okay, so now we are until the standing wave. So standing wave is where you, what we call, you as if the wave is frozen. So it's happened when we call the applied frequency match with the what we call with the natural frequency of the material lah, frequency. So other way is related to the resonance lah, resonance. That's why sometimes when you have the chocolate wrapper, ada chocolate tak? Tak ada. So for example, let's say this thing, I don't know lah. This, if you try to blow, sometimes you have what we call certain blow you will sound like a whistle out, right? So you try lah with the chocolate wrapper. So that is basically when you blow, the air vibrate. It's also, this thing also vibrate. The sound occur only when the vibration of your air match with the vibration of your whatever wrapper. So that's when you get resonance, you get the pitch like that. Okay, so that is basically this standing wave lah. Okay, so once we know about this type of the wave, okay, by the way, example of perpendicular is what? Perpendicular transverse wave. Example. Water ripple. Water ripple is mechanical, but it's also exhibit the transverse wave. Water ripple. What else? The EM, the electromagnetic wave, all the EM is transverse lah, because EM itself is this, is what we call the magnetic field combined with the electric field goes forward in what we call perpendicular angle with each other. So that is EM. So that is example of perpendicular. Standing wave is just when you when the wave seems frozen on air or whatever, is because when your applied frequency is equal to natural frequency. So you get also the name, also we call it ni lah, the resonance. Okay, now if you look here, you can see what we call, you know the wavelength, you are quite used with that because you can measure this thing. You can measure from here to here. You can measure. You take a ruler, you can measure. But here also you have also frequency. Frequency is basically Frequency is basically cycle. How many cycle how many cycle occur per period lah. Normally we use hertz. Hertz is basically the what I call the unit for frequency. Normally hertz is basically how many cycle per second. So meaning that here for the light, this light, they what we call 10 to the power of 15. What is this? 15 is what? 10 to the power of 12 is what? It's more than theta. So basically it's take radio wave lah. Take ni lah, microwave. Okay, microwave is what is? Mega is all like radio lah, radio. Radio you open the era, open the switch on the channel, 10 what you call? Let's say the Hot FM. Hot FM berapa? Hah? Tak dengar radio dah? What is the frequency for the, let's say, era? Last time we talked about era, right? 103.3 megahertz. Okay, so basically it's cycle. The wave that is you get from the era station onto your radio is vibrate this much, 100 million times per second. So that's very small lah, very small. Not very small. It depends also the speed, because this thing it just tell you how many is vibrate per second. But in order to get the wavelength, you need to have some relationship, because how to relate this to this? How come, for example, radio is here, right? How this relate to this? 10 to the power of 4 hertz relate to 10 to the power of 3 meter. In other words, how do you want to know what is the wavelength of the era? Era. What is the wavelength for this? So that, let me, what we call this thing? So there are equations for that relate the frequency and also the speed. So basically the, saya ingat dah. The speed is basically apa? Okay, the speed is basically the wavelength times the frequency. Frequency. So wavelength is basically lambda lah. Frequency we call it f. Okay. So because all the electromagnetic wave here, they travel at the speed of light. Okay. All the magnetic wave from here to here, regardless their wavelength, they travel same with the speed of light. What is the speed of light? What is the speed of light? Speed of light apa? Speed of light. How much? Speed of light. Anyone? Huh? 3 times 10 to the power of 8 meter per second, ataupun this meter per second, or 3,300,000 kilometer per second. Okay, so that is the speed of light. So because the EM maintain its speed, so you can find what is the wavelength here. So that the wavelength is basically what? Speed 3,000. Let's say we take this lah, 3 times 10 to the power of 8 milli per second, divide by 3.3 times what? 10 to the power of what? 10 to the power of, because mega 10 to the power of 6. Cuba kira. First, what is the wavelength of the era? So the top one is the speed of the light. The bottom one is basically the frequency of the era station here, 103.3 megahertz. So what is the wavelength? Because this is the formula to relate the wavelength here and the frequency. What is the wavelength? Rohani, apa wavelength dia? Kira. Siapa dah kira? Afiq. Berapa? Berapa? 3 times 10 to the power of 8 divide by 103.3 times 10 to the power of 6. Berapa? Ada berapa, Umi? 0.9. 2.9 apa? 2.9 or roughly 3 lah, 3 meter. So basically that is basically the wavelength. So for example, if let's say I have radio here and open the channel to era, so the wave is basically this. One complete wavelength, not one complete, yeah, half wavelength. It's not one complete wavelength because from crest to here, from here to here, is not one complete. Because if you want to have complete wave from here, so this is complete, this is complete. But when the wavelength is basically from here to here, so basically from complete lah. Complete lah, sama lah. Apa best pula? Sama lah. Yang tak complete tu notes. Notes tak complete lah, notes. Between notes is half. Between wavelength is complete lah, complete cycle. Meaning that the cycle is 3 meter here. So I open the radio here, the wavelength, the first is until here lah. Lebih 3 meter ni. Sampai 3 meter lah. So basically that's how you relate the wavelength and frequency with the speed. Okay. And so that is here, the frequency part and wavelength. And also you have here the, what else? The, previously I talked about the energetic or not, right? The sting is more energetic than this. This part is more energetic than this. So there are also relationship between this frequency wavelength with the energy. Okay? So that is this. So the energy, so this is another relationship. The energy is basically relate to the frequency, is proportional to the frequency. So the higher the frequency, the higher the energy. Okay? So this is basically proportional lah. So in order to find the exact correlation, you need to divide by you need to find the constant lah. So E divided by F is basically you get H lah. H, this is a Planck constant. So I go a little bit deeper in particle physics because later on, when we deal with something small like nano, the world of nano is governed by quantum physics, not the classical physics. That's why I need to go a little bit in this quantum physics. This is what I call Planck constant. Pernah dengar? Planck constant. Pernah dengar Umi? Tak pernah. So basically, it's like this. You know what we call the pi. Pi, you know pi. Umi tahu pi. Asyik Umi je orang lain lah. Siapa ni? Tak pernah ni. Asyikin? Iman. Iman. So you know pi, right? Pi. Pi is berapa? 3.142. So pi here, wherever you go, you use the same constant. So this is what we call constant lah kan. It's like this c, the speed of light, the constant, 3,000 km per second. How they measure it, don't ask me. But basically this pi, the constant, how they get this number is basically, the pi is basically what? It's basically you have the bulatan, the circle, and then this this circle, this is circumference, ukulele-ference. And this is basically the radius, right? Radius. So the pi, they got it by C divided by D. This is diameter. Circumference, you get pi. Regardless, your circle is this big, or this big. Imagine this circle. If you try to divide the ratio between circumference and diameter, always you get this 3.142. So that's why, because if you see the circumference, what we call the formula for this is what? 2 pi r, right? Okay. So the radius, the diameter is 2r, right? So you get 2 pi r divided by 2r, diameter, right? So you got cancel, you get pi. So that's how they get this constant pi there. Cancel, you get pi lah, you get pi. Same like this. In order to get the constant, in order to make the equation, because here it's only said that energy is proportional to the frequency, but it doesn't have exact equation yet. In order to find the exact equation, you need to find the constant, the Planck constant. So the Planck constant is basically, the value for the Planck constant is apa? 6.6 6.6 times 10 to the power of negative 34 joule per second. So that is basically what we call the amount of Planck constant. So when you got this thing, let me Yeah, let me close this thing. When you get this thing, you can make the equation exact again. So now when you correlate, you get E equal to HF. So this is the exact equation. This is just a proportional only. So now you still get the energy is proportional to the frequency lah. Energy proportional to the frequency. Okay, so this, when you know the energy here, okay, you can calculate lah because you get this value and then you get the frequency, you get the value. So the reason why people want to get this equation is that, for example, when you talk to phone, right, the phone use radio wave. You want to know because when you said that the phone is dangerous to your health, is basically you want to try to correlate whether the radio wave can go inside your body and damage the the cell. Okay, so they require certain energy. Okay, so basically for the okay, so for the DNA damage, for you to damage the DNA, so we start going a little bit to bio part now. In order to damage the DNA, you need 4 electron volt energy. It's another way lah to to talk about energy lah. I will not go detail for that. But this EV, electron volt here, you can correlate from this also lah. From this energy here, you can correlate with the electron volt also. So this, to damage the DNA, you need 4 electron volt. The what we call the radio wave, the phone radiation is basically 0.00000004 electron volt. The phone radiation come in form of radio wave because you are transmitting the radio wave, right? So that energy, they calculate using this, energy equivalent to this, and then they convert to electron volt. Because normally for physicists, they use this electron volt lah. So, but they have some correlation lah between this and this, just to say to you that this, your phone is not enough to what we call the energy coming from the radio wave from the phone is not enough to damage the thing, because for you to damage the DNA, you need 4 electron volt. More energy than this. Is 1,000,000 times weaker. Your phone radiation is 1,000,000 times weaker than the energy required to damage the DNA. Okay, so that's the thing. What else? What else I want to do? Okay. Okay. So any question now? So now what we have learned? We have learned about the, okay, we recap a little bit. We have learned about the type of wave, whether it can go to vacuum or not, and also category based on the how the medium travel. We learn about the longitudinal. We learn about transverse wave. We learn about standing wave. We learn also about this interference. This is what we call interference, when the wave combine with each other, or superposition. Another term is superposition. Another name lah. Superposition of the wave. And then we are looking at the how you can relate the wavelength and frequency and so on. And then we also see how you can relate this wave with the energy. That's why if the frequency is high, okay, frequency is high, the energy also is high. Okay, and if you look here, frequency and wavelength is inverse related. So if frequency is high, the wavelength normally, if the speed is same, you maintain. If frequency is high, the wavelength is basically lower lah. So that is the relationship between the wavelength, frequency, energy. Wavelength, frequency, and energy. And also we introduced the word about Planck constant. Okay. So when I say like this, you might ask, this doesn't look like this, like this thing. If let's say you have this thing, this is longitudinal. So if you, let's say you have the microphone here, and you convert it, you connect with the oscilloscope. So this, you still get something like this. Okay. So this, it can be transverse or longitudinal. It doesn't mean that this must be longitudinal, transverse only, okay? Because you can correlate, okay? It just you need to know that what is the difference between longitudinal wave and transverse wave, okay? The electromagnetic is always transverse, and even this, the superposition, even this one can what we call, can have this superposition. For example, I don't know whether I can see that. For example, let's say you have this thing. Let's say I have this thing, and then I have a low region, and then I have a dark region here. And I plus with something like this, what will get? What will you get if I add like this? What you will get? What do you think you will get? This plus this. Huh? Sorry? Lagi gelap. Oh, saya tak buka Tak buka alamak. Saya tak buka. Tak apalah. So you get something like this. Okay? You get more intense here lah. More intense here. More intense here. And then what we call? So this what we call same like this, constructive superposition or constructive interference. Okay, if the other way around, you get other way lah. Okay, you get something like this, and then you have something like this, and then now you have something that's difficult. Okay, so you have something like this. You get what? What you get? What you get if you combine this together? Yalah, what you get? What will you get? You just get like something dot like this. Dia pecah lah. It's like spread out. So this thing, whether it's longitudinal or transverse, they what we call, they sort of like can experience this destructive or constructive interference. So that is one of the properties of the wave. That's why if you have the light here, if you have torchlight here, and then you have another torchlight here, let's say this one is give a green what we call green light, and this one give you the red light, what will happen? It doesn't bounce, right? You get this thing and this thing, they just combine with each other, right? Nothing happen. Okay, but if you have like a ping pong ball, you go here, and then another ping pong ball here goes here, what will happen? It will sort of like bounce back, right? It will bounce back like that, and then that. So that's the difference between wave and particle. Between wave and particle, this is one of the unique properties of the wave. It can interfere. Particle cannot interfere. For example, like siapa nama? Umi dengan Iman goes near and near each other, and they will repair, right? Because they will not be superimposed with each other. But if, let's say, Iman and Umi is a wave, then they can just go through with each other like that. Just go from each other. Okay, so that is basically that part. So this interference is one of the unique characteristic of the wave. So I can put here. So we're done here. Just we add a little bit. So wave also. So you learn about interference. Interference. So this is one of the properties of the wave. Another property, there are many properties of the wave that is unique. For example, wave can also be reflection, can undergo reflection, and also what else? Diffraction, reflection. Let's say reflection, refraction, diffraction. And previously we learned about wave also can go absorption, and also the transmission. Wave also can be dispersion, can also scattered like that. So this is a few of the things that can happen to wave. What we learned today is interference. So absorption we learned before when I show you they are what we call, they are a molecule here. and then you what you call the duit. Ada duit? Duit balik? Ada duit. Rohani mas ni satu duit. So you have this thing. Let's say I do 3 things only. So this I explained in the previous class, but this time I have this lampu UV. Duit. Kesian Rohani. Saya kena pau je. Saya Afiq pun tak beritahu. Saya lupa. You bagi tahu sampai saya ingat. Aduh. So basically nothing. And then if let's say I do like this, you can see, you cannot see lah because you need to close the light whatever. You can see this thing, nothing. You can see that then, that thing lah. You can see the what we call the so number 1 there. So this happen if you have the normal light like that. You don't see it because there are not enough energy from the light to excite the fluorescent material inside the thing. Once you give UV, because you see UV, this is a black light. It's not a UV that can damage the. Normally the UV that you use to counterfeit or whatever is not like strong UV. UV, there are many UV, UVA, UVB, UVC, and so on. The one that you see in the lab, in the laminar hood, that is UV that is dangerous lah. The one that is very high, because UV itself, they are like a region. High UV, low UV. So you can see UV compared to visible, UV have like high energy because the frequency is higher, right? So because of that, it can excite this the fluorescent material in this what we call in this money, and you can see that thing. So the idea of absorption. So I recap a little bit. So the idea of absorption is that, let's say you have this electron here. Okay, when you are getting the UV from here, let's say UV in blue, let's say. So this excitation, okay, this thing, this electron can jump, excite, meaning that it's not like this electron will move slowly here. Quantum world, the word about quantum, what does it mean by quantum? Because I need to go a little bit about quantum. The idea of quantum is that the energy is quantized. You can see like this orbit, like orbit. So from here, let's say this UV is enough to kick this thing. It doesn't mean that this electron will move here slowly. No, it doesn't work like that. Quantum means this thing suddenly goes here. It's like suddenly. It's not like going slowly. It's just suddenly there. It just suddenly go to the high level like that. Okay. So suddenly goes to the top. Where is my green? So goes to the top, goes to here, and now you can go here also. It's depend on the energy, how much energy. Let's say the energy from UV is so high, so it goes to the double thing, and then when it goes at this higher level of energy shell, it will not stable, so it will go back. So you have two paths here. Either you can go from here, and then go to what we call. I mean, they go down cascade like that, or it can go straight away like this. Okay, it can go either this way, A, or B, or C, like this. Okay, if you look here, A, because it's different energy level, it have their own energy difference. It's like when you have a spring, let's say you have a spring. Ada spring, ada getah, tak ada getah. If you have spring, you try to pull, you store the energy, right? And then you push, what happen? The spring goes to you back. So what? Apa tu? That is interference. So, what's that? Ni kan saya tak tutup generator ke? Maybe saya tak tutup generator saya. Okay, so maybe that's interference, I think. That's interference. Anyway, here, A, B, and C. So between this and this have their own energy. So A, the energy here, like the spring, for spring it release what? Kinetic energy, right? you feel that when you have a rubber band, you pull and then you release it, they have energy. So same like this, it's release the energy, right? So this A might release what we call the different color than this. Let's say this is blue, and then B, green lah, color green, and then B, something banyak color ni. B, they also have their own what we call their own energy. Maybe when from electron from here to here, it will release the color instead of kinetic energy. In this time, it release the blue color, and here C, it release the what we call the color of red, like that. Just let's say lah. So meaning that every atom have their own specific spectra. Meaning that if you try to excite the atom, any atom, the energy that you give can kick the electron to certain higher level energy, and the electron can go back and give multitude of spectra. That's why if you see, let's say I go to this, let me put here atomic spectra. Let's say hydrogen atomic spectra. Ada tak? Saya tulis kat mana? Hydrogen atomic. Okay. So image. Lambatlah. Tak ada. Kenapa tak ada? Lambat. Slow. Okay. So you can see like this. If let's say you have the hydrogen, and if you try to look under certain what we call the diffraction grating, later we talk about the diffraction later on, you will see there are two colors. Do you know how people know, how astronomers know that the composition of this star and that star? So this based on this lah, spectra, this thing. Okay, because certain each atom have their own fingerprint. For example, if you shine that atom with the certain energy, you get the fingerprint like this. It's like your the atomic fingerprint lah. For example, this for hydrogen, you get something like this and this. Meaning that they are two, meaning that they are like roughly like this lah, more or less like this. They give green and they give red like that. So different what we call different material will release a different atomic spectra lah. So that's just about the spectra lah. So I think that's it for today. Today we talk about the properties of wave. We talk about some of the categorization of wave under vacuum, the way how medium travel, and also the type of the wave, the transverse, the longitudinal, the standing, and also the relationship between the wavelength, frequency, and energy. We also learn about something about interference, and also we discuss a little bit about the absorption here. And then maybe next class we close this wave chapter by discussing the reflection, and diffraction. And I think that's for the wave. Okay. So that's it for today. And the reason why we talk about this, because under tool later on, tool for looking at the nano, they use wave. Electron microscope, they use electron wave. The SRD using X-ray, and so on lah. Even the optical microscope use the light also the wave. So that's why we start with the fundamental.